ABC Calc, this is going to be your day 54 notes. Today we're going to be talking about the area between curves and where we headed just kind of in general with area under a curve. Here is a list of topics that we can apply to the concept of area under a curve. Today's topic is the area between two curves. We will eventually very quickly extend that concept to finding volumes, maybe taking an area and rotating it around some sort of axis to develop a volume. Where we will develop a formula that represents the length of a curve, which is awesome that we can find that length. The physics concept of work we'll talk about and how that relates to area under a curve, center of mass, and then a lot more to come when we develop chapter 6 here. So to get started in thinking about area between curves today, we're going to use something cool on the calculator called the shade option in the draw menu. We can actually shade the area that we're talking about between two curves using the input shade y1 comma y2. This will shade the area that's above what's in y1 and below what's in y2. So right now I have typed into y1 x plus 1 and then 9 minus x squared in y2. So if I hit graph, not too surprising that this is what the graph looks like. And what I want to do is I want to shade what's above y1 and below y2 to find the area between those two curves. So when I quit the screen here, if I go to second program, that draw menu, and choose option 7, which is shade, we can shade alpha trace y1, comma, alpha trace y2. If you hit enter, it's going to go to your y equals screen and shade the appropriate area. How awesome is that? So what we want to figure out is how can I use our techniques of integration to determine that area between the two curves? Okay. So just as a quick visual, when I did shade with y1 and y2, we had this function here. We had this function here. And we saw that the shading was this region here. Okay. How do we determine that area of that region of the graph? Well, to find the area bounded by the y1 curve and the y2 curve and lines x equals a and x equals b, here's my diagram right here. Okay. So I want to find the area that's bound by these two curves in between and on the interval from a to b. So of course we're going to divide x into subintervals. Okay, n subintervals. So we're going to take this b minus a length and divide by n, such that that would be the width of each rectangle, delta x. The width of the kth rectangle, somewhere along the interval, would just be delta x. The height of the rectangle at that value, x sub k, would be f of 1 minus f of 2 of c sub k. And therefore, the area of that rectangle is the difference in those heights times our delta x. So therefore, if we apply this over the course of the entire interval, take the sum from k equals 1 to n of the heights times the width, delta x, along the way, that would represent the total area. And of course, taking the limit as n goes to infinity represents this Riemann sum as the definite integral that we know from a to b of the difference in the heights along the two functions times the width dx, which, using the function notation that I have up here, it would be the integral from a to b of the top curve f1 of x minus the bottom curve f2 of x, find those heights, and then times dx there. So probably what you would have expected anyway, to find that shaded area, find the area to the top curve minus the height at the bottom curve, dx. And then we can go from there and apply that to examples like the first one on the next page. Find the area bounded by the graphs of y equals x squared and y equals x plus 2. So let's make a sketch of the graph off to the side here. We get y equals x squared. And then y equals x plus 2, linear function with a slope of 1, y-intercept of 2. It's going to look something like this. I'm going to find this area right here. So in order to find that area, we have to figure out what are the values of a and b that we're integrating. So in other words, what are the x values for these points of intersection? Well, we can find that pretty easily by setting our functions equal. Let x squared equal x plus 2. Find the x values that we're integrating along. So we're going to get x squared minus x minus 2 equals 0. Factor that to x minus 2 and x plus 1. So the bounds on our integral are from x equals -1 to x equals 2. So when I go to set up our definite integral, we're going to set those bounds -1 to 2. And to find the area between those two curves, we have to figure out what the top curve is minus the bottom curve. So the top curve is the linear function x plus 2. And from that, we will subtract the quadratic function x squared. So it's going to be x plus 2 minus x squared dx. Okay, so then from there, it's really all about finding the antiderivative, plugging in the bounds. So it's going to be x squared over 2 plus 2x minus x cubed over 3 from -1 to 2. And if you plug in the bounds here, you're going to get 2 squared over 2 plus 2 times 2 minus 2 cubed over 3. Minus plugging in -1 for all those x's, so -1 squared over 2. And of course, this algebra part you guys should be able to do hopefully pretty easily. Just being careful about your work. Use the calculator as needed. When you plug in 2, I'll tell you this all simplifies to give you 10/3 minus, and then this would simplify over here to give you a -7 over 6. So if I add those together, subtract a negative, make a common denominator, that's going to be 20 over 6 plus 7 over 6 for 27 over 6, which reduces to 9/2. Okay, so if we were to type this into the calculator in Math 9, I hope we would confirm that we would get 4.5. You guys can double check me on that. But certainly we should be able to have the skills to evaluate this by hand, plug in the bounds, and simplify from there. Okay, so check this out right here. We have two curves, and it's a little bit tough to see maybe which one's which. So I'll try and highlight for you that the function f of x, I'm going to sketch in blue. It's this one right here. And then the function g of x, I'll sketch in red. And that's this one right here. And as I'm sketching these, I hope you see what I'm probably going to be getting at here. If you want to find the area between those curves from A to C, if that's your goal, well, the problem with just integrating straight up from A to C is that the function that's the top function changes at some point on the interval. It changes at x equals b. So I can't say for the entire interval from A to C that one function is above the other. So you would have to separate this into two different integrals. From A to B, you can see that the blue function f of x is higher than the red function g of x. So to find the total area from A to C, you would just break this up and say, first, let's do the integral from A to B of take the top function f of x minus g of x dx. And then you would add on the rest of the area between the curves from B to C, where now the top function is g of x minus f of x. Okay. So drawing the picture, if it's not given to you, is going to be critical, because you don't want to just assume that for the entire interval you're finding the area over, that the one function is always greater than or equal to the other. Now, in the example up here, once I drew the picture, we had no issues. Based on those points of intersection, the linear function always above the quadratic there. Okay, but depending on the functions, certainly this would be a likely scenario. Okay, and you can see those rectangles drawn in there as evidence that, yeah, the height of this rectangle right here is going to be the blue minus the red height, and then this would be now red minus blue. Okay, so let's see if we can take a look at the next example. It is actually our final example, and we're going to find the area using two different methods. Find the area enclosed by y squared equals 4x and y equals 2x minus 4. So if we're thinking about y squared equals 4x, maybe what we're thinking is, or at least I hope what you're thinking, sideways parabola, y squared equals 4x. If you're unsure about that, if you take the square root of both sides, you would get y equals plus or minus It's going to be 2 times radical x, and y equals 2x minus 4. So if we think about the sketch here, two radical x and then negative 2 radical x would form that sideways parabola that I've sketched. And then for y equals 2x minus 4, that's a line that has a negative slope and a negative y-intercept and a positive slope. So that's going to look something like this. So we want to figure out the area between those two curves, which is this section right here. Okay. So let's see. To find the area between the curves, well, we're going to have to find our points of intersection here along the way, right? Well, here's what's kind of weird. If we think about doing top minus bottom, look at the start of our interval for this area. Top minus bottom is going to be for the same equation, isn't it? In fact, I don't get to the top minus bottom being two really different functions until I get, or my blue and red function, I should say, until I get beyond this point of intersection. So let's find that point of intersection, because that will actually make a big difference in the way that I calculate this area. We're going to wind up, just like the last picture I showed you, set up two different integrals to calculate our area if we want to use, by the way, vertical rectangles, where I take the height of the top minus the height of the bottom. Okay. So let's see, let's set plus or minus 2 radical x equal to 2x minus 4. Okay. Maybe dividing out the 2 might make things a little bit easier. So we get x minus 2 equals plus or minus the square root of x. Square both sides. So then this becomes x squared minus 4x plus 4. Squaring radical x is just going to give you an x. Subtracted over, x squared minus 5x plus 4 is now equal to 0. And then factoring would give you x minus 1 and x minus 4. So the 2 points of intersection that we get are at x equals 1 and x equals 4. Okay. So we know that this right here is at x equals 1, and this other point here is x equals 4. So if I want to find the area from 1 to 4, it's definitely this top blue function minus the red function. Okay. But what we have to be, I think, a little bit cautious about is that the initial area that I'm finding from 0 to 1, this shaded region, is the top of the radical minus the bottom of the radical there. So if you're going to use vertical rectangles here to represent your heights, the height here, one function minus the other, is different than the height if I come over here, which functions we're subtracting to get those heights. So to evaluate the integral, you're going to set up the following. You're going to go from 0 to 1, first and foremost, of the top blue radical function, which is 2 radical x, minus the bottom function, which is negative 2 radical x. So that would actually turn into a plus 2 radical x there, right? When I subtract negative 2 radical x there, dx. So that's the first part of this area in this region. And then from 1 to 4, then on that interval, you can take the top radical function and subtract the linear. So you would take 2 radical x and subtract 2x minus 4 over that interval, making sure that we distribute the negative appropriately and kind of go from there. So I would say go ahead and finish this one out. If you want to try it by hand just to get more practice with finding integrals, go for it, or at least Math 9 to double check your work. What I want to show you is whatever you get up here is your answer from checking. We should get the same answer for method 2, but for method 2, we're going to use horizontal rectangles. So if I draw that same exact region again, I'll show you how horizontal rectangles might actually make our lives a little bit easier. So here we go with our 2 radical x and negative 2 radical x, and the line 2x minus 4 looks like this. Okay. So if we use horizontal rectangles, what we're doing is we're taking our rectangles and we're drawing them like this. Okay, so what I have to do now to find this area, if I'm using the rectangles that are horizontal, is we're comparing it to the y-axis. So I have to readjust the bounds here, because now my bounds of integration are this way along the y-axis, and we have to readjust our functions. If we're integrating with respect to y with these horizontal rectangles, we have to get our functions to be x equals in terms of y. So our originals are y squared equals 4x, and then y equals 2x minus 4. So really quickly, x would equal y squared over 4. And then over here, you would get x equals y plus 4 over 2. So if you integrate these curves with x equals in terms of y, the right curve minus the left curve dy, that would equal the exact area that we calculated up here. But hopefully you can see why it's a little less complicated to do it this way, because you don't have to break this up. The right curve, the y plus 4 over 2, is always to the right of y squared over 4 over this interval along the y-axis. Okay. So to find these y values, you can plug in the x bounds and figure out what y equals at those values, but this would be at -2, and this would be at +4. So you're going to integrate from -2 to 4, the right curve, which is y plus 4 over 2, minus the left curve, which is y squared over 4. And this is now a dy example. And it'll take some time to get used to that. We're so used to integrating over an interval along the x-axis, but you can certainly integrate over an interval on the y-axis if you're solving it x in terms of y, get these y functions that we subtract, and we're going right minus left back to the y-axis here. Okay, now even though we're integrating these functions that have y's in them, there's nothing saying that when I type this into the calculator, I can't use x as the variable to sub in there. So just to save some time, I will Math9 this and confirm the area. If you want to try it by hand, of course, you may go ahead and do that. But if we do Math9 from -2 to 4, the function y plus 4 over 2, you can change that to y over or x over 2 plus 2, and then minus x squared over 4 dx. The area between those curves winds up equaling exactly 9. So if you had already stopped and done the area up at the top, you should have gotten 9 as your answer. Okay. If not, go back at this point, confirm that this area is also 9. And then, although it'll take a little while to get used to using dy instead of dx, see if you like this method even just a little bit better. And we'll get a little bit more practice tomorrow in our notes, getting really used to this concept of using horizontal rectangles to draw and find the area, as opposed to maybe vertical rectangles, especially when you have to break it up into different intervals. That does make things a little bit more challenging. Okay, that's it for today. Have a great rest of your day.